Hello, everyone. Thank you for joining me today on this talk on request reply integration pattern. Uh, this is the last day and the last talk of the conference. I hope all of you were able to make good use of the conference and got some good sessions to attend to. Those of you I have not met before, I'm Anuraag Verma. I'm a technology manager with Goldman Sachs in Salt Lake City. And I'm mandated to build a communication platform for sending client communications to our wealth management clients. Our platform is built using Spring Boot, MongoDB, and Apache Kafka. And we use messaging-based integrations in some parts of our implementation. And one of the use cases we solved using request reply, and that's basically the basis of today's talk. So I'm sure most of us, if not all of us, are aware of design patterns, and we use that in our day-to-day implementation. But there's another facet called enterprise integration patterns, which is about techniques of building distributed systems and integrating them together. Uh, this talk borrows heavily from a book by the title Enterprise Integration Patterns by Gregor Hopp and Bobby Wolf. They had written this book, I think, sometime in early 2000s, but the practices that they detail in that book hold true even today if you're building a distributed system. Uh, So some of the key takeaways that you will have from today's talk is about building an understanding of the request reply pattern and some best practices around it. Some of the error handling techniques that you could use if you're creating a messaging based application. And also you'll be able to identify and leverage some of these techniques in your own implementations. So in today's talk will cover about the use case. I will introduce the use case that we had to solve. We'll cover some of the basics of the request reply integration pattern. We'll cover some of the strategies about dealing with errors in such implementations. Then for the problem that we had solved, we'll talk about some of the design considerations that we had to deal with, and some of them actually did lead to some very passionate, interesting conversations within the project team. And then we'll look into the system design that we had, which was implementation over Apache Kafka. So from the use case perspective, in the wealth management business at Goldman Sachs, we have been on a digital transformation journey for the past couple of years. We have created a brand new client website. Among the many features there, one of the features which we enable our clients is to look for all the documents that they have received from us over their relationship with us. Our product had a very simple ask. They wanted this search feature to be performing. They wanted no matter how many documents the client has, he or she should be able to search for these documents under 1 second on the website. Honestly, on the new technology stacks on which people work today, that's a pretty fair ask, but we had some problems. Uh, we had about more than 30 million documents which were sitting in multiple legacy data stores, which by nature were non-performing. Each of these data stores had their own data model of describing a document. They did not enforce a consistent taxonomy, due to which the search, aggregation, and presentation of the search results to client was unable to scale and be performant. So solution for us was pretty straightforward. What we needed was a centralized data store, which enforced a unified data model. It needed to be performant and it needed to be highly available. We wanted the data store to be optimized for the search use case because that's a problem that we were trying to solve. We were willing and we were okay to pay penalty if it takes us longer to write these documents into the data store. Also, as part of the build up, we had to ensure that all these 35 million documents in the legacy stores get migrated into the new centralized data store, and same continues to happen as new documents get produced. They should get returned to the centralized data store. So before we start going into how did we actually solve for this use case in our implementation, let's go over through some basics of the request reply integration pattern. So what's a request reply integration pattern? It's basically a pattern that you will use when you have a process which is publishing messages or events. It is interested in observing results of that requested action, and it is okay to do it in an async manner. That's when you will use a request reply integration pattern. So what are the building blocks of this pattern, right? You will obviously have your messages, which will be your request and reply messages, which will bundle together your payload with some header information or the metadata about the request. You will have some request and reply channels, which will be used for communicating between processes. And obviously you'll be having processes which are acting as requesters and repliers. So it's a pretty straightforward pattern. A typical flow will be that the requester will create a request object with the payload and some header information. It will package or bundle that into a message or an event. It will write it on the request channel. The replier will receive this message. It will do some validation on that message. It will unpack the payload, take the necessary action as requested. Once it has the results that it needs to send back, it will package that into another message, which you can call a reply message, which will have the response payload with some header information, which gets written on the reply channel, and the requester will receive it. Of course, if anything goes wrong, then those messages have to be handled, and maybe an option is to send them on an invalid or an error message channel. Right? So this becomes a little more interesting when you have like multiple requesters talking to different systems, right? So your requester, there are multiple requesters which are interacting with the replier. How does the replier know which reply has to be sent to which requester? One of the techniques that people use is that they will embed that logic in the replier itself. That replier will look at the request payload and make the determination where should the reply be sent to. That's one option. Some other people take the approach that they will say, just like the request channel, I have a single request channel, I will have a single reply channel as well. And I will let the requesters deal with the complexity of figuring out which reply they want to consume. Obviously, both these approaches come with some deficiencies. In case you're embedding that logic in the replier, you have to deal with continuous change, that anytime a new requester is coming or the requester is changing, your replier needs to change as well. In the second option, when you're creating a unified single reply channel, some of your requesters may not like that at all, and they will not want to be co-located with other requesters for a variety of reasons, because they have varied use cases. They don't want to commingle their data with another system. So if you look for the solutions for this, your solution actually sits on how you send emails today. If you look at your email headers have a reply to placeholder, which basically allow the sender of the email to specify how he or she wants to receive the reply. So same concept applies in this pattern as well. Requester is recommended to put in a reply channel, and replier will basically look at that information and accordingly route the reply to the right reply channel. Benefits of this approach is you get the isolation between replies for each of your requesters. Plus, your replier doesn't, in case your replier creates a generic implementation for sending these replies on the appropriate channels, your reply is not changing every time a new requester is coming or a new return address is being specified. Moving on, another consideration you have to take into account is how do you map the request and replies? Like I said, that this is a implementation use case that you follow when you're using an async implementation pattern, which basically means at the least your requester is not blocking on the same thread on which the request was sent out. So likely it's listening for replies on a different thread. It could be it could very well be different set of processes, or it could be different set of machines on which requests are being published and replies are being expected. So how do you link a request and reply together? Also, you need to factor in that this pattern does not guarantee that replies will be received in the same order in which the requests were published. So you need a mechanism for linking these things together. The recommendation for the solution for the problem is that you should ideally embed a header on your request, which is a unique message ID for every request that is being published. And the reply will play back the same message ID as a correlation ID on the reply, enabling the requester to map a reply received to a request which was sent out a few seconds or with whatever lag it was sent out or whatever time frame earlier it was sent out. So benefit of using this is if you consider a system implementation where you have multiple systems, let's say you have a system A, which is acting as a requester for the system B, which in turn is acting as a requester for system C. You can create a full execution path of that request by linking these message IDs and correlation IDs together. And it can help you in tracing the life cycle of a request. It can help you with debugging. It can help you with a number of things. So let's quickly look at the message structure. A typical request message, a bare minimum, what it needs to be, it needs to have a message ID. It needs to have a timestamp when the message was created. Obviously, the request message will not have a correlation ID because it's being originated at that point. It will have a reply coordinate, which will tell the reply where the reply should be sent out. And then it will have some payload, which you can bundle into a payload or a content field, right? Your reply message will have its own unique message ID. And this basically allows you, as a requester, you can talk to the reply system and you can say, I received this message. This is the key you gave me. Can you tell me what originated that, right? It will have its own timestamp when the reply was created. It will have the correlation ID, which is matching this reply to the request. It won't have a reply coordinates, but it will have the result of the requested action being sent back in the contents, right? Another thing I like to throw in the reply message is the correlation timestamp, which I find very useful actually, because that way, if a requester wants to see how much lag or how much processing time it took to complete a request, the requester has both the timestamps available in the same reply message, and they can run any kind of metrics or diagnostics on top of that. But generally, you should feel free. This is like your opportunity to make your message headers as complete as possible. So if you want to play back like host information, some traces information to create like spans for similar to how distributed tracing work in HTTP world, this is the place where you can get creative and you can start adding those fields. Some other recommended patterns which we actually didn't have to use but could be useful is message sequence. This is when the messages or event you're publishing are not isolated messages or events, but you're publishing group of messages which should be considered to be processed together. So you can use message sequence by embedding a size and a sequence number into your header. And then it can be used for enforcing some ordering with respect to how the requests have to be processed, or also used to ensure that all complete messages are received before the processing is initiated, right? Another useful thing that I find is message expiration. So let's take some examples for message expiration, right? Let's say you're using this pattern for a payment use case. A client is trying to make a payment. You own the payment system, but you want to run a payment authorization check with another system which specializes in that. So you will publish a message. In the message, you will embed some metadata which will tell the authorization system that I'm expecting to receive a reply for this authorization request within 2 minutes. If I don't receive within 2 minutes, I'll consider that client has denied the payment and I'm going to deny the payment. So you can embed an expiration timestamp on the header. And on the authorization system side, if you are not able to process the request in 2 minutes, you can very well not even give any reply back to it, because your contract with the payment system is that you will give replies within 2 minutes. Otherwise, they can consider it as an expired or a timed out or a denied request. Again, your use cases, you can play with it the way you want to. Okay, let's quickly go through like some of the other handling strategies. So when we started working on our first messaging implementation, which we were doing on Kafka about like 5 years ago, one of the points where we spent a lot of time discussing and debating was how to deal with bad messages. Now, Kafka as an architecture doesn't give you features like RabbitMQ, where you have like error queues and dead letter channels. It leaves it up to you as a consumer of Kafka to decide when you want to accept bad or error messages. You can do many things here. You can, anytime you get a bad message, you can reject it altogether. You can push it to some other topic. You can push it to some other data store. I think a general best practice, which is recommended, is uh, in order to protect your consumers from bad messages, you need to ensure that you push any bad message or failing messages into a dedicated error channel, and you come up with your custom implementation on what you want to do with it. Generally, if you're using a dedicated single error or bad message channel, you can use a static retry strategy, and you can retry any failed message on a periodic basis based on your use case. But sometimes that's not enough, and sometimes you need to do more than that, right? So let's consider another example before we go into where a variable retry strategy will be useful. Let's consider an example that you are, let's say, a trade booking system, uh, and you are dealing with multiple price providers to get the best prices. Let's say, for whatever reasons, you need to apply different, as a price provider system, you want to apply different algorithms or different SLAs with respect to how soon the price has to be provided back. So in that case, if some system, which is truly a trading system, is asking you for the price before the execution of trade, maybe your SLA will be that you need to return back the price within 5 seconds, within 10 seconds, right? But if there's another analytical system which is trying to get a price for running some analytical models, uh, you can likely give it price back with more delay. You can go as slow as, let's say, 1 minute or 2 minutes. So in that case, having a single error topic will not work for you. And what you need to have is you need to have dedicated multiple error channels. And based on the nature of the request, you can either push it back to an error channel, which has a retry policy of, let's say, every 5 seconds, or another error channel, which has a retry policy of, let's say, every 1 minute. Another pattern that you can use with a variable retry strategy is to use a back-off algorithm, which is anytime a message fails, for the first time, it will go back on a topic which retries every 1 minute, let's say. Uh, if it fails a second time, then it will go back on a retry channel, or sorry, on a other channel, which retries every 5 minutes. And you can have a third channel which lets you retry every 10 minutes, and then you can have a dead letter channel. So you can decide a variable back-off algorithm, and you can do it without blocking your threads on that back-off algorithm by just putting it in a different queue, which is persistent, and your retry consumers can run on that. So let's talk about some of the considerations that we had to deal with for our use case, right? So like I said, when I introduced the problem, that for us, the use case was that we wanted a data store which is performing for search, not necessarily performing for write. So one of the challenges that we had to deal with was the system throughput that our data store was giving us. Kafka will allow us to run 100,000 millions of records at a very high rate, but our downstream system will not allow us to write as many records as frequently. So we had to do some rate throttling to make sure that we don't overload our downstream system, the data store, and create some contentions on that. So that was one consideration that we had to deal with. Just because you have a Ferrari doesn't mean you can drive it on Main Street at 200 miles per hour, right? That's the problem. Second thing was the availability. Sometimes your downstream systems will have their planned downtimes or maintenance in which they'll say, while I will stay available for you to come and read data, I do not want you to come and write data on me because I'm recreating, let's say, all my indices, right? Or I'm doing some other housekeeping work. So we had to deal with how to ensure the quiet time on our implementation so that when the downstream system is in a maintenance mode, even if someone is trying to come and write documents into that data store, we can pause that process behind the scenes without any tech involvement. Second concern, which I think is pretty common with messaging implementation, is how to ensure exactly once delivery versus idempotent. So the new version of Kafka obviously gives you guaranteed exactly once delivery. You just need to turn a few more knobs on your Kafka implementation to get it. Or the other option is to create your consumers which are idempotent, and then you don't really have to rely on Kafka to give you the guaranteed exactly once delivery. And again, you have to look at the trade-offs on based on your use cases, what works for you. For us, the idempotent consumer made more sense as opposed to using Kafka's exactly once delivery. Other interesting thing is about error handling, right? How to deal with poison pill if someone gives you a bad message, which will cause your consumers to throw exceptions and die. How do you deal with that as opposed to dealing with transient failures, which may happen because a downstream service is temporarily unavailable, right? Second was how to deal with retry policies. What kind of retry policies do you want to enforce? Do you want to go with a static or a variable retry? Do you want to have a back-off retry policy implemented using your messaging infrastructure, right? Uh, very related to the retry policies, how you want to deal with order in which the updates have to be applied, right? In today's world, everyone works with the concept of eventual consistency. But what if it does not work for you, or what if the updates are applied out of order? You cannot guarantee eventual consistency. So that's another consideration you have to deal with, and we actually have to handle that in our implementation. And then the last concern, I think, is with respect to in this async implementation, when you're creating all these retry policies, what kind of statuses do you want to give to your consumers or the requesters? Do you want to let them know only once after all the retries have exhausted, whether their request was success or failure? Or do you want to tell them at every failure whether what's happening on their request? Or you want to use a hybrid approach where only after certain retries have failed, that's when you want to notify them with respect to what's happening on their request. So let's quickly jump into the system design that we have, right? So like I said, we had multiple data sources which had their own data models. Data was different documents were sitting in different data stores. So that's where we start. What we first of all did was look at all these data stores to come up with a unified data model, which was agreed upon with all the participating teams. And it was data producers' responsibility to now start writing enrichers and transformers to convert their legacy data into the unified data model. Each consumer had to write their own enrichers and transformers. Then we set up our own dedicated one single request channel, because once you get a unified data model, all the requests will start following a common request structure, and that way we can have a single request topic on which we can receive request. So each data producer was writing their publishers to publish request to the request topic. On our side, we had a request consumer, which the first thing that the request consumer will do is to look at the messages and do some validations to weed out any bad messages right away. So anytime you get a bad message which is not adhering to the contract, it will get rejected right away by publishing a error reply on the reply topic. In case the validation goes through, it goes through a processor which will take the request and write it on our new centralized data store. Now, once you attempt that right, obviously you can have two results. You can either get a success or failure. Let's talk about failure first, because failure is a little more interesting. Any failure will get written on the error publisher first. as long as they are pending retries on that error message. If you have already exhausted all your retries, then it gets rejected and it gets sent back as an error response on the reply publisher. The any bad message which get published on the other topic, we had a fixed retry policy, so they will get retried, let's say after a fixed interval, and then they go through the same life cycle of validation and processing a second time. Every time you retry a message, the pending retries get decremented so that at some point you will exhaust all your retries, and your consumer or your data producer will get to know that the request has exhausted and we cannot write it onto our central data store, and they can take whatever subsequent action they wanted to. One thing that we introduced in this implementation was a concept of early act, which a consumer can opt in to receive an early act to their request, and that allows us to control at what frequency do you want to send an error message, and you can give a transient error message back to the data producer, which tells them, I have your request, I encountered an error, but I'm still gonna continue to try writing this message into my central data store. And that way they can control what they want to do with respect to if they want to show their users a message, if they want to hold off some processing from happening on their side, they can look at these reply messages and take necessary action. Now, on the success part, obviously, once you get a message success from the processor, it gets published on the reply topic as a success message for your data producers to consume on the other side and allow the next steps of the processing to go through. So one thing I'll call out here, like even though we recommended that like every data producer should get its own dedicated replies, in our use case, because all these applications were sitting under one single business unit, there was a lot of engineering collaboration. People were okay to use a single reply topic, but we still created a generic implementation with a futuristic view in mind that if tomorrow we get a use case where the consumer said, I'm not comfortable dealing with a single reply topic where I'm co-located with every other tenant, we did create the flexibility that they can set up their own consumer specific reply topic, and we will additionally publish their replies on that topic as well. So this was the whole system design that we did, and we were able to run the full volume of historical documents on this implementation with, I would say that we did not actually have to deal with any kind of technical challenges with respect to post-implementation, dealing with performance issues or dealing with any exception scenarios. This is all that I wanted to cover today. So I can pause now in case anyone has any questions. We can take those questions now.
Yes, there is one question. Let me read that to you.
Okay.
Question: is the unique message ID generated when the message is created, or can you create and specify your own unique ID before you send it?
Okay, so it is basically left to the it is left to the requester on how do they want to deal with message IDs, right? People can either use a primary key from the data model and say every request's primary key will go as message ID. If someone wants to use a UUID, which a lot of people find it useful today to just generate a UUID and stamp it on the message, people can do that. So it's completely up to the requester based on their use case, how do they want to use it. Okay, if there are no more questions, go, maybe we can close the talk.
Yeah, I think we're good. Okay, thank you, Anuraag. Thank you for your dedication and support. Hope to see you next year.
Yep, thank you everyone for making time for this talk.
Bye-bye.
Bye.